Good evening. My name is Dr. Shakti, and we are going to go to the next chapter in physiology. So we already covered with your general physiology. Next, we'll start nerve muscle physiology, and I'd have to say this is a very important topic. Your first semester exam will largely be related to questions from nerve muscle physiology and hematology, and maybe transport from general physiology. Okay, so we'll just go ahead and understand few concepts about your nerve muscle physiology. So in the first class, we're going to be talking about a few things. This is again a very important topic. And not only is it important exam-wise, but understanding the concept of it will help you understand CNS by large later in the third semester. Okay, so we'll be dividing the class today first on a calculation because questions can come for the exam for your spotters where they'll give you some basic things, and from that you have to calculate. So you have to know the calculation, you need to understand how it works. So that is your Nernst equation for getting your equilibrium potential. Okay. Then we'll try to understand the concept of what is your resting membrane potential. Again, this comes as a short note, and if you look at the textbooks and if you look at the answer papers of students, mostly students do not have enough points to write this as a short note. Okay, so that is where I'm going to help you out in understanding what all to explain over here and what is the concept behind RMP. Then, if it's part of an essay, usually you can get a sub question called graded potential. And then, of course, your main action potential. Okay, so one, understanding equilibrium potential. Then we'll talk about your resting membrane potential. Then what is the graded potential? What is an action potential? And if time permits, we'll go for properties of nerves. So in a combination of all of this is how an essay will come from this. Okay, so maybe a clinical scenario will be there, or multiple sub-questions of answers will be there. One can include RMP, one will include action potential, one will include something about properties of nerve. So I hope you're getting what I'm trying to say here. So these are basically the different headings under which we'll be talking today. So first about your equilibrium potential. What exactly is equilibrium potential? In order to understand that, you need to first start off by understanding a little bit about your basic ions, which are there in your extracellular fluid and your intracellular fluid. And I'd have to say, understanding this will make understanding electrophysiology easy. Okay. So you have the extracellular fluid, you have the intracellular fluid. So this is your ICF, this is your ECF. In your ECF, the predominant cation which is there, that is your sodium actually. Okay, so the positively charged ion which is more predominant is sodium. If you look at it inside the cell, the positively charged ion which is more in number is potassium. Okay, now we have to understand the concentrations. This you have to learn the value. Again, lot of differences in different textbooks. Standard textbooks itself have few differences based on the conditions under which it was recorded and all. I'm just going to stick to one standard textbook at your level so that there's no confusion. I'm going to give you what it is also. So basically, we'll be taking values from Guide 10. So in case somebody asks you, what is this value? Where did you get it from? Guide 10. Okay. Again, multiple versions of the same values are there in different textbooks in different conditions. Okay. So, sodium extracellularly is around 142 milliequivalent per liter. Okay, so I'm not writing the unit over here, but it's mainly equivalent per liter, just for your understanding. Inside, it is around 10. Okay, potassium inside is 140. Outside, it is around 4. Okay, so what does that mean? If I were to open up a transporter, any sort of channel over here, by normal diffusion, sodium would ideally try to go inside. Potassium would ideally try to go outside. This is the first thing I want you to understand. So the major extracellular cation is your sodium, major intracellular cation is your potassium. Second point, the major extracellular anion is your chloride. The chloride, if you look at it outside, is going to be 103. And inside maybe 4. This again depends on the type of cell, but usually in muscles and all, it is like 3 to 4 and all. But, in Guyton value, that's what I'm giving you. So what would happen if you open up a chloride channel? It will try to go inside. Okay. So major extracellular anion is chloride. Major intracellular anion. So this is where there might be a little confusion. I've seen MCQs where a lot of people make a mistake. So inside we have protein and we have miscellaneous phosphates. Which is the major? If that is the question, then the answer has to be phosphate. Around 75 is outside and inside, and 4 is outside. Protein comes to around 40 milliequivalent per liter, in milliequivalent per liter. Okay, if it is in gram per deciliter, it's around 16. So if it's in milliequivalent per liter, protein is 40 and outside it is 5. Okay, so if I were to open up an ion channel for phosphate, phosphate would try to go outside. If I were to open up a channel for protein, protein would go out. But protein does not go out because protein is generally a larger structure to be, carried out through ion channels. Unlike all these other ions, protein is a much more larger molecule and it usually does not go out like this. Okay, so I hope you're with me till now. So the major extracellular cation is sodium. Major extracellular anion is chloride. The major intracellular cation is potassium. Major intracellular anion is actually miscellaneous phosphate. Okay, next thing is the intracellular anion, which is responsible for your Donan effect. That is going to be your protein. So now we have to understand what exactly is this Donan effect. Okay, the Donan effect. So this tells that if you take a membrane and between the membrane you put different particles. If there is something that is non-diffusible through the membrane, impermeable substance through the membrane, okay, and there are diffusible substances. So basically, this presence of non-diffusible or impermeable substances will determine the flow of the permeable substances actually. So it's not as simple as you'd imagine. Okay, so for example, I'll give you this example. Potassium. Okay, and we'll take protein. So when you have to maintain some charge neutrality, You always talk about a positively charged ion and a negatively charged ion. Both of these are inside. So imagine this is permeable to potassium and it is impermeable to protein. A membrane like that. Okay. So what is going to happen is you take a membrane, you take a cell, you take a lot of potassium. Now, these potassium positively charged ions, which are there inside, you take it out. It goes by itself, as I was telling you. Okay, positively charged ion, more inside. So if you open up a channel, it'll start getting more and more outside. So positively charged ion, based on the concentration gradient, just went outside. Okay. Now, along with that, a negatively charged ion has to go out. The protein which is there, which is negatively charged, will try to go out, but it cannot go out because it is too large. So now what will happen? All these positively charged ions that are accumulating at some point will create a potential with this negatively. If everything was permeable, you wouldn't have this problem. If a positively charged ion is going, a negatively charged ion is going to go. So you wouldn't have this problem of a membrane potential existing. But such a membrane potential just existed because of this Donan effect. Inequitable distribution of ions. Because of the presence of a non-diffusible ion. And that will result in a membrane potential which is generated. Okay, so as we were talking about a concentration gradient, which is allowing this to go that side. Now, this membrane potential, which is developing, is something that is going to oppose this. With time, what is happening? More and more positively charges are building up on the other side, which is creating a membrane potential. And as the membrane potential keeps on increasing, at some point, this flow based on concentration gradient will be negated by this membrane potential until no net movement is happening. I hope you're understanding this. So what I'm trying to put it out to you is that this membrane potential at which the flow based on concentration gradient is negated. That is what is called equilibrium potential. Okay. So again, there is a particular membrane potential. So as you keep going on, the membrane potential can keep on changing. But at one particular point, as the membrane potential keeps building up, okay, so something is coming from this side, it keeps on coming. Eventually, a membrane potential will develop from this side and start opposing it. At one point, the membrane potential will develop so much so that it will oppose each other, even though a concentration gradient is still existing, but there is no net flow. Okay, so this is a very important concept in understanding action potential. So this particular potential at which there is no net movement of ions is what is called equilibrium potential. Okay, so historically speaking, when various experiments were done, if you take a look at your membrane, there are multiple ion channels which are there in the membrane. But initially it was difficult to isolate, everything. So there were certain patch clap experiments which were done where you take only single ion channels. And then they study the properties to understand what is this potential. How much is the concentration, what is the potential and all that. Okay, so for a single ion species, Okay, a single ion species channel. If you're only talking about one single channel, then we can use a particular equation called the Nernst equation to get the value of this particular equilibrium potential. Okay, so that is the point at which no net flux is going to happen. That potential, when the membrane potential reaches that level. Okay, so that is the first thing that I was talking about, the calculation. So what is the Nernst equation? The Nernst equation is given as equilibrium potential is equal to RT by ZF natural log concentration inside by concentration outside. Okay. So this F is basically your Faraday's constant. R is your gas constant. T is your temperature. In a human body, what are we concerned with? 37 degrees Celsius. That is your body temperature that is always maintained. So this whole thing at 37 degrees Celsius, you know a constant value. This is a constant actually. It'll come to around, 26.3, something like that. What is the natural log? 2.3 times your log 10 is what is a natural log. So ultimately, this equation can be written at 37 degrees Celsius as, plus or minus is there, plus or minus 61.5. Okay, so this RT by F just got replaced by 61.5. Not only RT by F, that natural part of log also. So 61.5 divided by Z. Since we remove the natural part, it's only log 10 concentration inside by concentration outside. So this is the final equation that you have to understand. So when you get the question, they'll give you the concentration of the substance inside, concentration of the substance outside. And you should know the valence. Like for example, Na plus versus Ca2 plus. So what is the valency of that? Based on that, you put the value here. Okay, so only these three things will be given. And you can easily find the value. Okay, so this is the equation that you use for getting your equilibrium potential for a single ion channel. But the thing is, if you take a look at the whole membrane, it's not only one ion channel which is there. There are multiple ion channels which are there. So over there, there is increasing importance of permeability, relative permeability, which is there. So that is where when multiple ion channels are present, use another equation which is called Goldman-Katz equation. Hodgkin-Goldman-Katz equation. Okay. So here it's going to be something similar where equilibrium potential equal to concentration of a substance like sodium plus concentration of a substance like potassium plus concentration of a substance like chloride. These are the major contributors for your ions actually. To take a look at your osmolarity. Okay. So sodium, potassium, chloride is there. Now, this, I told you, is not the only thing. We have importance of permeability. How much is permeable to what? For example, if certain things are more permeable, their impact on that equilibrium potential will be higher. Okay, so again, it's very difficult to go to detail, at your level. All you have to understand is the equilibrium potential of a membrane in where you have multiple ion channels which are involved. that will basically be based on which ion is more permeable, which has more resistance, which is more permeable. That is what I'm trying to tell you, along with your concentration gradient. Okay. So this into the permeability of that substance. Permeability of that substance. Permeability of that substance. So this is in the numerator. Okay, so I'm just going at it one by one, step by step. Now, we were telling substance concentration, which is inside. Only chloride, you make it outside, because this is a negatively charged particle. And you do the ulta down. Concentration of sodium outside into the permeability plus concentration of potassium outside into the permeability plus concentration of chloride inside into the permeability of chloride. I'm sorry if this, sounds very complicated. I assure you it's not. It's actually the same thing, concentration inside by outside. But permeability is also involved, and three total ions are also involved. And only thing is, because positively charged ions, the negatively charged ion, you make it ulta so that the positive negative value comes properly. Okay, again, they will not ask you questions about calculating using this for you. Only this will be used. But if a question of equilibrium potential and all is coming, then you might need to mention this equation. That's why I'm giving it to you. Okay. So with that, we understood what is an equilibrium potential. This concept is very important in order to understand whatever we're talking about in the future. Okay. We'll come to understand what is called a resting membrane potential. So we have a cell. It has a membrane. So remember, I was talking about a membrane having multiple channels. So that means you have to use Goldman-Cass equation for that. Okay. So what is the RMP? That is, at resting state, what is the membrane potential which is there? At a particular resting state, what is the membrane potential that is there? That is your resting membrane potential. And we notice that compared to sodium or chloride, maximum permeability is there for potassium actually. So somehow in your cell, in neurons, there is potassium leaky channels which are present at rest. So major contributor to your resting membrane potential is going to be this potassium ion, because that is more permeable compared to everything else because of the presence of these leaky potassium channels. So just tell me, when potassium is there, potassium is higher on the inside, how much was it? 140. And outside, it was around 4. So what will happen if you open up, okay, or there's presence of a leaky potassium channel, potassium will go outside. Now potassium will keep going outside. Will it keep going forever? No. That is what I was talking about. That is the concept I was trying to explain over here. Potassium will keep going until it reaches the equilibrium potential. So after that, even if a concentration gradient is there, it will stop going ahead. Okay. So at a resting state, the membrane potential, if you were to record it, it usually comes to around minus 90 millivolt. Okay. Now I'm just going to go back to your Nernst equation. According to Nernst equation, you're taking a single ion species. You take sodium, you take potassium, you take chloride. If you look at the equilibrium potential of sodium, it usually comes to plus 60, 61 and if you look at a chloride, it's going to be minus 70 millivolt. If you look at potassium, based on the temperature again, all of this will vary, minus 90 millivolt. What do you understand from this? Some based on different temperatures again can go to 94 and all. Some standard textbook have different values. That is just based on the difference in the temperature that is measured actually. So some textbooks again, as I was telling, say 94. So potassium is minus 90. Okay. Now let's come back here. Your resting membrane potential, usually in cells like your skeletal muscle, your cardiac muscle. So in these cells or large neurons, generally your resting membrane potential is around minus 90. So again, it starts making sense because why? Your potassium is the major leaky ion according to Goldman-Katz equation. So somehow the equilibrium potential will be closer to that. At rest, everybody is trying to achieve its equilibrium. Okay, so the membrane potential which is here will be closer to the equilibrium potential of that ion species, which is more involved over here. So what is the main reason for your resting membrane potential? That is your leaky potassium channels. That's not all. Okay, so if I were to put the values of all of this in Goldman-Katz equation, you see that out of this minus 90, you get a value of minus 86 millivolt by Goldman-Katz equation. Now we're confused. According to Goldman-Katz equation, it should ideally come to minus 86, but we're getting minus 90 millivolt. How did that happen? So this is where you have to understand two things in RMP. RMP is generated by your leaky potassium channels. The remaining minus 4 millivolt is by your sodium potassium ATPase. So RMP is maintained by your sodium potassium ATPase. How does this work? So it is minus 90. Imagine there is some positively charged ion like sodium, which accidentally came in through some non-specific channels. So some extra positive charge will come. So that is basically what we're talking about. It's not like, your membrane is only with potassium. You have chloride, you have sodium. So sodium is a major contributor to whatever else is there. So according to that, it's coming to 86. But your RMP is still 90 because even though a little bit of sodium and all that comes, the sodium potassium ATPase now acts. What does your sodium potassium ATPase do? Takes the sodium outside, brings back potassium. That potassium again can go out. So ultimately, whatever extra sodium is coming in can be pumped outside to maintain your RMP at that level. That is what your sodium potassium ATPase is doing. So when you talk about RMP, you can talk about your Nernst equation, you can talk about equilibrium potential, you can talk about your Goldman-Katz equation, then talk about your leaky potassium channels that generate your resting membrane potential. Talk about how, according to Goldman-Katz equation, it is only minus 86 millivolt, which is done by your Katz equation, but the remaining minus 4 millivolt is actually by your sodium potassium ATPase. Hence, potassium leaky channels are involved in the generation of RMP, and your sodium potassium ATPase are involved in maintaining your RMP. Okay. Now you can give examples of your resting membrane potential. So as I was telling you, usually minus 90 is your resting membrane potential for your skeletal muscle, cardiac muscle. Typically large neurons. Around minus 70 millivolt is going to be, smaller neurons. Minus 55 millivolt will be smooth muscle. Okay. If you take a example of your RBC membrane, there it can come to minus 9 millivolt. So these are just examples of different resting membrane potential you can talk about. Okay, so next we have enough points to write under RMP and explain it. Now that RMP is done, you have to understand two concepts. What is graded potential? What is action potential? So at resting state, this is how everything is going on. And it is maintained also by sodium potassium ATPase. So as I was telling you earlier, influx of some positively charged ion is the problem. So this is where you have to understand what is a graded potential. This in different systems will have different terminologies. Something called a receptor potential. You'll have a term called end plate potential. Okay, so you will have the same terminology in different chapters throughout physiology, named as different things. But ultimately, what it is a graded potential. So what exactly is a graded potential? Say some sort of a stimulus is there that is not reaching a threshold. What is the threshold? We'll come to that. But say there is a stimulus and a particular strength is there and it is not reaching the threshold. So what happens is this stimulus which is coming from outside will stimulate some positively charged ion and make it activated, resulting in influx of your positively charged ions like sodium. Okay, it will result in influx of positively charged ions like sodium. So when positively charged ions are now starting to come in, what will happen from minus 90 millivolt? Say this went to minus 70 millivolt. But as we told, your sodium potassium ATPase will now act to bring it back to minus 90. That means this is not something that will keep on going. Okay, momentarily, there is a small potential which developed, but that will soon be fixed. That is basically what graded potential is. So graded potential are, first of all, localized. It's not like you stimulate this part and it'll keep going on like an action potential. It'll only be localized to this area and a few areas around it, and it won't go beyond that. It is localized, non-propagative. Okay, localized, confined to a particular area, and it is non-propagative. And it can be of two types. This can be either because of an influx of a positively charged ion or negatively charged ion. So it can be a cap electronic graded potential or an electronic graded potential. So that is it about graded potential. So graded potential are just localized things that do not keep propagating and eventually will die off. So it does not result in an action potential yet. Okay, so your cells keep getting stimulated, neurons keep getting stimulated. Doesn't mean every time it gets stimulated, it'll go into action potential. Most of the time, it'll go into a graded potential. Only if the graded potential keeps going down and reaches a particular threshold level, then only action potential will develop. So how will this look? If, for example, this is the membrane potential, then membrane potential minus 90, it's just going on, minus 90. From minus 90, it went to minus 70. It went up and then it was brought back. Over. This is the diagram for your graded potential. Instead, we make it into an action potential. So I'll just draw a diagram of my action potential first. Then we'll describe it. So you give a stimulation at some point. Usually, after the stimulation is given, a small gap is there before it starts coming, which is called latency. Then you'll see something like a graded potential curve beginning, which we are talking about. If the graded potential reaches the threshold, then it'll go into a spike potential, acutely going up. And then it'll start coming down again. And once it is coming down, at some point, it'll slow down like this. But it does not go back to the RMP. Instead, it continues to keep going down. And then comes back to RMP and stays there. This is how an action potential is. Okay, so again, what I was telling you? One, there is, when you give a stimulus, there is what we call a latent period before the effect is seen. Then there is a period where slight slowly increasing, similar to what is graded potential. If it does not reach threshold, what will happen? This will become a graded potential and come down. Since it reached the threshold, it resulted in a spike potential from here. From here, it resulted in a spike potential. Now, after the spike potential, it is coming down, and at some point, it'll start slowing down. Now, instead of reaching this and stopping there and continuing in your RMP, it is gonna keep going down and it'll come back. And after that, it'll stay there. So this is basically your action potential. So how do you define action potential? These are brief sequence of changes in your membrane potential. Remember your membrane potential that I was talking about earlier? This membrane potential, brief sequence of changes in the membrane potential. So these are basically based on certain recordings of the membrane potential. So from minus 90, this value over here is say minus 45. This will be somewhere 0. This will be plus 30, for example. Okay, I'm just giving different values for your guidance. So brief sequence of changes in your membrane potential when a threshold or above threshold stimulus is given. This is how you define action potential. So what exactly is action potential? These are a brief sequence of changes of your membrane potential when you give a threshold or above threshold stimulus. If it's below the threshold, then it will not become an action potential. It will become what? A graded potential. So now let us go and dissect what exactly is happening at these various stages. What are they called? So again, the first thing, you're giving a stimulus. Once you give a stimulus, that stimulus has to now open up an ion channel. It should get carried through the membrane and reach inside to activate it. So all of that is basically the latent period. In a nerve, when you stimulate it, the time that is required for the opening up of the ion channel is the major time that is there. And for the flow of, after opening up, there will be a flow of ions. And that flow of ions should result in change, and only then it will get picked up in your recording. So all that is basically your latent period, which is there. Then I just draw one cell over here for you to understand. So this depolarization current, what it does is it opens up non-specific ion channels, because of which sodium is gonna basically come inside. So positively charged ions are gonna increase, making the membrane potential go up. The same thing that we saw in, graded potential. So from minus 90, it can go till minus 45. Say for this membrane, minus 45 millivolt is the threshold. So this is where you have to understand, when you reach the threshold, there are particular separate sodium channels which are existing over here, which are called voltage gated sodium channels. So these channels have a particular gating mechanism which covers it on top. And only when it reaches a particular membrane potential will it open. So it basically detects your membrane potential. When it reaches a particular membrane potential, it opens up. And that membrane potential, when it opens up, is basically a threshold potential. Once it reaches the threshold potential, your voltage gated sodium channels open. Now, voltage gated sodium channels open means more sodium is going to come in, which means more positively charged ions are going to come in, which means membrane is more going to be above your threshold level, which means more sodium voltage gated sodium channels keep getting opened up. And this is like a example of a positive feedback reinforcement. What is happening? Sodium channels are coming in. That opens up a voltage gated sodium channel, which means more positively charged sodium channels are coming in, ions are coming in, making the membrane potential more positive, making the voltage gated sodium channels to keep opening more and more and more until it keeps on coming in. Okay. Now I'll ask you another question. Why is this graph that I'm talking about going up like this? That is because we were talking about different ion species. Till now at RMP, maximum permeability was for potassium. Now we have another channel which got opened up, because of which permeability for sodium is much, much more now. So when you take a look at equilibrium potential, the major contributor for that equilibrium potential is going to be sodium. We all want to be in an equilibrium all the time. Okay, we don't want to be stressed. We don't want, excess pressure from one side. It'll be nice if we can just relax. That is exactly what sodium is also trying to do. Sodium has a concentration gradient which is there. It'll keep on going to the other side until the membrane potential from the other side makes it equal and opposite, and it reaches its equilibrium. So, what is the equilibrium potential of sodium? Plus 61. I talked about it earlier, remember? Equilibrium potential of sodium is plus 61. So, what is happening is, from minus 90, which was equilibrium potential of potassium, it is trying to go towards the equilibrium potential of sodium. It keeps going up. It goes to 0. It then goes and crosses 0. That is called the overshoot. So this whole phase is what we call depolarization. From here to here, this is what we call depolarization. In this depolarization, we have from here to here spike potential. Okay, and the part above this is what is called overshoot. Above 0 it went. Why? Because it's trying to go to plus 61. But in this diagram, if you look at it, it's not going to plus 61. Instead, it's going to around plus 30 and then coming back. So now what happened? So this happened because this stimulus which is coming from outside, which resulted in a configurational change and made sodium come in the first place, that same stimulus, why is it not acting for other ion channels? It is acting for other ion channels, especially if sodium and potassium is also getting activated at the same time. But because of the mechanistic differences between these ion channels, potassium takes a longer time to open up. So this is one concept I want you to understand. That same stimulus which is coming from outside is stimulating both sodium and the potassium ion channels. It's just that sodium is faster. So it got opened up faster. Now it's trying to go to its equilibrium potential. It's reached somewhere around plus 30. By then, our slow guy got activated potassium and he decided to start now. What is potassium's equilibrium potential? Minus 90. So do you think it will allow it to keep going towards plus 61? It'll try to drag it down now towards its equilibrium potential. And by this point, what will happen? Your sodium channels, which got opened up, will start shutting down. So in this phase, your potassium channels going down. Equally, it's trying to reach the equilibrium potential of potassium. So this is your repolarization. So during repolarization, there is one particular part of the repolarization which is called after depolarization, where you see a slowing of the repolarization. Why does this happen? This happens because, it's going towards its equilibrium potential. What is driving it? Basically, your concentration gradient, which is there. This concentration gradient is what is basically driving the movement. Now, as it keeps on going, at some point, the concentration gradient will reduce. Remember in general physiology when we learned about Fick's law? So what was that? Delta C. So the flux, rate of flow of the flux is proportional to delta C into area by thickness. So that delta C, if it is greater, more the flux or rate of flow. But as more of it kept going to the other side, what happened to delta C? The concentration gradient reduced. So at some point, because the concentration gradient kept reducing, the flux reduced. So that is what you see over here. And this is what is called after depolarization. Kindly remember, it's not after repolarization. Although it is coming at the end of repolarization, by nomenclature, it is called. That is because of some error which happened long time back based on recordings actually. But it's still going on like that. Okay, I'm not going into the detail. Basically, olden things that used to record used to come ulta. That is how the recording used to happen before, not like how it is now. So based on that, some nomenclature problem. That is how it's still called after depolarization. The name continued actually. Okay, so we have your graded response, spike potential, overshoot, repolarization, after depolarization. Each of this you should be able to explain. This is an essay, mind you. Okay, 5 marks, you have to explain just this action potential cut diagram. So what is the reason for latency? What is the reason for the graded response? Why a spike potential happened? Why it's going towards the overshoot? Why repolarization happened? Potassium influx. Why depolarization happened? Sodium influx. Then why is after depolarization happening? Because the concentration gradient is reducing, the flux is reducing, and the rate of flow is reducing. Next, as it is going down, instead of stopping at RMP, it goes into after hyperpolarization. Okay, instead of going into RMP, it hyperpolarizes. So that is happening. That also you have to explain. That is happening because these potassium channels which were opened up, it's not like, a tap system that we have in a body. Okay, just imagine there are multiple, millions of, channels which are there. Now you open up all the channels, potassium is going in. Okay, who's there waiting and getting ready at the exact moment it reaches minus 90 to go and close all the minus 90 cup, all the potassium channels at the same time? It's impossible. So once it reaches there, it'll try to close the potassium channels, but there'll be a slight delay. It'll take some time before all the potassium channels are closed. During that, in the meantime, little bit of potassium kept going outside more than what was required, and it went further ahead. That is the reason for hyperpolarization which is happening. Then your sodium potassium ATPase, all that comes and it brings it back to your normal RMP level. Okay, so this is basically your action potential, different phases of action potential. So we talked about your graded potential, we talked about your action potential. Because of lack of time now, I don't think I'll be able to do properties of now today. Okay, I'll try to do it in the next class. So this is what we've done so far. Very important conceptually to understand it. To learn from the textbook in detail, you will not understand so much. Okay, so one, about Nernst equation. You understand what is an equilibrium potential. Then using that concept, understand what is an RMP. Then when a stimulus is given, which is not reaching a threshold, graded potential. And when it reaches threshold, action potential. Define action potential. Draw the diagram of action potential. Explain what is the reason for each phase. 5 marks. Okay. So for those of you who are interested, I want you to understand a little bit about the platform Auricle. So Auricle has, recorded classes which are made available, which at your own convenience, according to how you want to study, you can take different topics actually. So you can do it at your own pace and go through it. So that is the recorded classes which are there about your entire physiology, anatomy, and biochemistry. Recorded classes are there in depth, at least from physiology perspective, I done around 100 hours of lectures have been taken. We have light classes like the one you have actually attending, where you can come and have, one-on-one doubt clearing sessions. We have a separate exam module which is there. So after all this, just before your exam, if you need to revise quickly and understand what are the important points, you can go for your express exam module, where the whole syllabus is covered under 20 hours or so. Then higher subscription plans has other things which are added, like one-to-one doubt clearing sessions, hard copy notes which can be made available for all the topics, which includes a lot of diagrammatic representations, MCQs, questions, match the following, okay, and a lot of fun zones and trivias and all that. And there are also question bank with different difficulty of questions. And these MCQs are not only important for your university, but in your future, you can also use it for your NEET, PG, FMG, next, whatever is happening. And of course, it's not only the theory, you still have to prepare for practical sessions, for which also we have recorded sessions and live sessions also before the exam. Will revise through the practical and what is important for the exam. These are the various subscription plans which are available. You can use my code Dr. Shakthinag 20 for discount on subscription. So thank you for watching. For those of you who are interested, these are the various social media handles where you can contact Team Auricle for anything. All right. So thank you. See you again next class.